My name's Brian Barrett. I'm from Sandia National Laboratories in the Scalable System Software Group, and going to be talking about data transfer in Open MPI and some of the structures and interfaces involved. So a real quick introduction, and then talk about some of the MPI communication models, because it helps phrase the background. I know this isn't an MPI talk, but an awful lot of this was driven by choices made by the MPI forum, so it helps have some background. And then a quick Open MPI overview. Actually, that's not the quick part, that's the long part. And then some quick future plans at the end, talking about what's going to be changing from what you find today if you grab the source code. So first, some thanks. A number of the slides and diagrams that I'm going to be presenting were borrowed from previous talks and kind of made to fit this, but a number of people deserve thanks for slides that have been presented and borrowed. So George Basilica from University of Tennessee, who's the Open MPI Datatypes expert, Ralph Castaigne from Greenplum, Galen Shipman from Oak Ridge, who did a lot of the InfiniBand BTL work, and Jeff Squires from Cisco, who's one of the kind of overall architects of Open MPI. So with that being said, let's jump in. MPI has 3 different communication models. The first, which is the most common, is point-to-point. And in addition to being the most common, this is the communication model that most drives the design of the communication subsystem in Open MPI, the BTLs in particular. So MPI provides an ordered tagged messaging system with wildcards. So what's that mean? Well, ordered means that if I send a message, 2 messages from rank A to rank B, they will show up in the same order on B as you sent them on A. Now, there's some constraints on that. That means they have to be on the same communicator, and you can think of a communicator as a communication channel, but a communicator is a nice structure with some other meaning we'll talk about later, and the tags have to be the same. Tags, meaning that in addition to the channel semantics that you normally get with, say, TCP, you can pick and choose messages out of order as they're received based on a tag that's set on the sender side. The receiver can choose to receive, say, tag 1 messages or tag 2 messages, and it'll get the first one of that tag. And then the wildcards is where things get tricky. For both the source and the tag of an incoming message when you post to receive, you can wildcard. You can say MPI any source or MPI any tag, which says you don't care about the tag or the source. For the source, that's not too big of a deal. The tag that really limits some of the structures for matching that I won't talk about here, but that much today. But there's a whole lot of message matching to keep that ordering that the optimizations are fairly limited that you can do because of these wildcards. One of the painful bits of MPI point-to-point is that it allows unexpected messages. That is, I can call send, and the matching receive doesn't have to be posted yet. Now, if you're used to TCP, this makes perfect sense, right? You call send, and later on you call receive, and receive doesn't actually do anything unless there's data that's already arrived, and then it gets copied out of the kernel buffers into your user space, and off you go. MPI pushes hard for a model where you don't copy into kernel buffers. It's designed around the concept that you should be, if your hardware supports it, able to send directly from the user buffer out over the NIC and to the remote side. This obviously, being able to send an unexpected message where there is no place to land the data on the remote side drives some design decisions that'll become really apparent later in the talk. And I should say send and receive have both blocking and non-blocking variants, meaning that you can call a blocking send that doesn't return until you can reuse the buffer, or a non-blocking return send that you then have to wait on later. The semantics are a little different than, say, a non-blocking send in TCP, where you call send, and it just sent what it could and tells you, okay, this is how much I sent. Because MPI revolves around messages instead of streams, what you actually get is a handle back that then you can ask, did this message send? And it'll say yes or no, and if the answer is no, you ask again later, did this message send? And so on until it says yes. So that's point-to-point in, that's about 50 pages of standard specification in 2 minutes. So I'm sure I missed some stuff there, but this is fairly well specified, and there's a bunch of books and user manuals on the web. That's probably a good starting point. So in addition to point-to-point messages, which are a single send and a single receive, MPI has collective communication. Collectives are very common in scientific computing. For instance, you may want to, at the start of an application, one process sends out the parameter set that you're going to use for the whole process, and it calls a broadcast. More common and more useful is that during each iteration of, say, an iterative solver, you do what's called an R-reduce. Everybody contributes a little bit, and you do a sum or a product to decide whether you're done. And there's a whole list of collectives, and for the most part, and there's blocking and non-blocking variants, and for the most part, in terms of the parts of Open MPI that we're interested in today, the low-level transports, these aren't important, other than their messaging traffic looks a little different than the point-to-point messages, in that frequently send buffers are reused. On a broadcast, you'll send a whole bunch of peers out of the same buffer, and that looks a little weird from the communication layer. The other places we'll talk about, we talked about tags for point-to-point. Open MPI took a weird design decision that you'll see sometimes in the lower layers, where the tags, positive tags, are defined to be by the MPI spec for use by the user. We use a negative tag space, so if it's a negative number, for collectives and a couple of other things. So you may see negative tags flying across the wire, and it can confuse. We've had a couple of times where people will come say, why do we see these negative tags flying across the wire? This has to be a bug, right? And no, it's a collective operation occurring. So for the most part, you don't have to worry about them unless you're trying to use MPI. And then the final one, communication model in MPI, is one-sided. And unlike point-to-point, where you have a send and a receive, as the name implies, in one-sided communication, you just have one side participating. You can do a put, you can do a get, or you can do an atomic operation. In MPI 2, there were fixed remote accessible segments, so every process would say, okay, here's the memory that can be a target to one of these operations. That got loosened a little in the recently passed MPI 3, but for the most part, it's these put and get operations with explicit synchronization operations to say, okay, I want all the memory spaces to be consistent now. Kind of like if you're familiar with doing threaded programming, kind of like a memory barrier type semantic. It has a well-defined memory model, which is a talk all on its own, in that it's multiple pages of some of the worst standards text you can possibly imagine. The good news for this talk is that we don't have to think about it at all. So if you're interested, it's written down somewhere, and if you're not, we're not going to talk about it here. The thing that is interesting about one-sided for this particular talk is we'll talk about some of the prepare source, prepare dest semantics, which are meaningless now, but semantics of the lower level communication driver. And one-sided has a unique property in that it tends to create communication buffers and reuse them, as opposed to point-to-point, where it tends to create them and destroy them as you go. And so this is one of those places where it's a use case very different from normal BTL use cases that has caused trouble. So we'll talk about that some more. But that's MPI communication in 10 minutes. Again, that's a summary of about an 800-page document in 10 minutes. So I missed some things, but they're not important for this talk. So the important bits are Open MPI's implementation of these semantics and how they drove the design of the byte transfer layers, the low-level communication layers for MPI, which are the parts that are interesting to this audience. So at a very high level, Open MPI looks like this little box, which hopefully showed up well on the projector. So you have a user application that's trying to do some MPI work. You have an MPI API that's smashing some things into just doing argument checking and smashing some things into a common API. And then you have a set of components, which Jeff talked about earlier today, about our component infrastructure. And important ones, we talked about point-to-point. There's a component called the PML that implements point-to-point logic. There's a framework called Call that shockingly implements the collectives frameworks. The OSC, or one-sided communication, implements all of the one-sided communication. And then there's the byte transfer layer, the BTLs, that are just kind of our low-level device driver. One thing I won't talk about very much past this slide today is that Open MPI actually has two low-level device communication interfaces. It has the BTLs, which is what we'll focus on today, because it's widely useful. And these are a fairly generic interface for communicating that encompasses a wide variety of networks. We also have what we call the matching transport layer, which is a framework for communication libraries, for network interfaces or network communication libraries that include a matching concept in them. And there are very few of these networks. They tend to be only for the high end of HPC, of high performance computing. Examples of them are there's an MXM library that's starting to gain traction that's part of the Mellanox InfiniBand stack for InfiniBand networks. There's the PSM, which is slightly getting defunct, but it was the network layer for QLogic's HPC network before they were bought by Intel. And then I had to talk about this a little bit because there's also one called Portals 4, which is a networking API that Sandia designed. But these are largely designed, these MTLs are largely designed for places where you have custom designed networks for HPC. So you don't run into them a lot in this environment. So we're mainly going to focus on the BTLs, which encompass networks we're used to dealing with. TCP, shared memory, UDP if you wanted, things like that, where it's a common stream or datagram-based network. And then there's all kinds of support interfaces, which is where we're going to start talking about because they, again, drive a lot of the decisions. So the first thing is what's in a name. So everything obviously we need some way of naming an endpoint. In TCP, this is an IP address, right? Or possibly a host name that becomes an IP address. That works great if you have IP. A lot of HPC systems don't have IP. IP addresses are also a fairly terrible way in terms of space efficiency for resolving a name. They're fairly, they can kind of get in the way of, you have to block them in 255 or 256 entry groups because of the octals, and it can kind of get a mess when what you really want is node 1, 2, 3, 4, 5 because you have a tightly integrated system. And we frequently want a job abstraction on top of that, and so the first name that we have is what we call the Orte process name T. This is a structure. The structure values can be compared. The value is important, not the structure and memory itself. That is, you can make copies of the structure and nothing bad happens. How these are generated is outside the scope of this talk, but Ralph would be the contact point for learning more about how those names are generated. Those are identify an individual process in the system, but they don't give you any scoping of that process in terms of how it relates to other processes necessarily. From a high-speed communication standpoint. For that, we have what we call the MPI Proc-T, or the MPI process. The MPI process stores a lot of information from an MPI standpoint, including for every connected process. That means any process that can communicate with each other will have a peer's MPI Proc-T. These are never copied. They are always passed by pointers. The pointers are comparable, but you never make a copy of the actual structure. There's one instance, there's a dense array of these things, and what you actually get when you're addressing is a remote node is you pass the address and then it looks up in the one global array. This allows you to do some caching of structures that have to be shared, very quickly looked up and shared between different components of the system. So there's a lot of useful information in here from a communication standpoint. I should point out these are probably going to move a little bit as we move the BTLs, which we'll talk about at the very end, but these are all pieces of information the BTLs need to talk to each other. So the first thing is pointers to opaque communication structures. When we're using the BTLs, this is a pointer to a BTL-specific endpoint that might include the socket if you're using TCP, or the queue pair if you're using InfiniBand for the remote node you want to talk to. They also include architectural information. For instance, is this the same architecture as I am? Is it big endian or little endian? Is it IEEE floating point or one of the other kind of IEEE floating points that you run into? Things that are important for HPC that if you're just moving bytes around may not be as important. It also has a data type converter. We'll talk about this in a second, more about this in a second, and some processor affinity flags. Again, we'll talk about more in a second. And then the Orte interfaces, so the runtime interfaces tend to use an Orte process name. The MPI interfaces, and therefore the BTLs and the PML, tend to use the UMPI functions, the UMPI process. It's fairly easy because they have different types. If you get the wrong one, you get a nice compiler warning. So that helps significantly. So we talked a little about addressing in that we have names. So how MPI actually identifies remote processes starts with the concept of a communicator. And a communicator you can think of as an all-to-all channel between a set of processes. You can have multiple channels in between any two given processes in the system. You generally start out with three, actually. Did I get that right? Sorry, you start out with two in MPI generally. One channel that's all the processes that you started with, and another one that's just you, which actually is useful for a number of interfaces. But then from those two, you can build up or split down until you get to subgroups that can be useful if you're doing, say, 3 or 4 different solvers, or 3 or 4 different problems at once, or your problem naturally decomposes, or there's all kinds of ways from a science standpoint that you would want to use these that are in no way important to communicating. But they're useful MPI structures in that they give us a place to hang stuff, right? So the first thing it gives us is this channel identifier that we make sure, you don't need to know how. There's a long algorithm that's well documented if you want, but that we use to make sure that you keep a globally unique identifier. There's a local and a remote group. These are a semantic that's kind of unimportant, but basically what you need to know is there's a structure that identifies every peer in this communicating channel. The collectives are chosen per communicator using the component system Jeff talked about this morning. And so there's which communicator or which collectives component you're using for this communicator. So if the communicator only has processes on the same shared memory node, we're going to use a different collectives algorithm than if there's one one MPI task per node across the entire system. And so those are cached on this communicator structure. And then the PML gets to store things about a communicator on the communicator. And we store some useful information there we'll talk about later. So I mentioned that a communicator has a group. And the group is a set of processes on a node. So you can manipulate them, but basically what you need to know is it's a set of processes, and they hold the pointers to the UMPI processes that I talked about to start, which then hold the information about how to actually talk to that remote process. So kind of to review, what you end up with is you have these communicator structures that an MPI process thinks about as how to talk to a communication channel. These can share or have different groups, which are the set of processes you can talk to. There's a global list. Actually, there's per process. Each process has a list of all the UMPI proc-T structures for processes it's connected to. And this is a dense list. So the groups have pointers to these. So if I get a communicator, if rank 0 is told by, if the application says, I want to send to rank 1 in communicator A, it would look at communicator A, look at its group, and then index off of that. The first thing would be this proc B, and this is where I keep all of my endpoint information for like TCP addressing. And so that's how you get from a communicator, which is what the user sees as his communication channel, down to the endpoint information that you want. Now, for the most part, the PML does all of this dereferencing for you. And what you get once you get to the BTL, and we'll walk through this as we go, is going to be endpoint information in this structure. And so that saves an awful lot of things that you have to understand in all this structure if you're working at the BTL level. But it's useful to understand how you got there. So that's process naming. The other place that's kind of useful, cloudy stuff that you have to know about to start playing with the BTLs, is the progress engine. So Open MPI has a central progress engine that triggers callbacks to registered functions. So anytime in the run, at any point in the runtime of Open MPI, a given component or framework or whatever can say, I need to be called, I need this function called at some random interval. And I do say random because it's dependent on what the application is doing. If the application isn't entering the MPI library, this progress function won't be called. But this is when the user says, OK, I want MPI to do something useful. So there's a couple of ways to do it. One is to just register a function. And in Opal, if you search for Opal progress, you'll find a nice header file with all the functions you want to use. It's really simple interface. There's basically an Opal progress register, and you give it a function pointer, and an Opal progress deregister, and you give it the same function pointer. But you can register a new progress function to be called, or there's an event library that's more complicated, but you give it either a timer saying, I want this to fire every approximately 1 second, or I want this callback to fire when this file descriptor is ready for reading or writing. The first is very easy. It's this register deregister. The second is fairly complicated to use, but a lot more powerful in terms of capabilities. And again, Ralph is the right contact for talking about the event library and how to use it. In currently, its primary user is the runtime, and therefore he's done a lot of work with that. So that's progress. Again, it's fairly simple. It's all callback driven when the user enters the library and says, I want something to happen. And so that's kind of a hard model to work with for a lot of BTLs, in that you can't expect to have something interesting happen every second, right? It might be every second. It might be every 10 minutes if that's how long the user goes between entering the MPI library. And so from a BTL standpoint, this makes for some interesting trade-offs that we'll kind of talk about as we go along. So the kind of one of the other high-level things that we have to know about are MPI data types. So MPI, like I said, is all about messages. So you describe the buffer you want to be sent as a single message, and then on the receive side, you say, okay, I want the data delivered here when the message arrives. Unlike, say, so with TCP, generally, when you call the send function, you give it a pointer and a length. You can also send it, use IOVEX and send a bunch of pointers and lengths, right? MPI takes that to the next level and has a complicated data type engine that allows you to describe exactly what you want sent. And rather than describing it in terms of byte lengths, which for scientific computing is often very difficult to deal with, particularly in Fortran. I don't know how many of you guys have ever programmed Fortran before, but they don't have a size of function that works real well. And so even knowing the size in bytes you want to send can be kind of difficult because you have to compute all these things, the way you first did when you first learning C and no one told you about the size of function, where you look up in the table and say, okay, an int's 4 bytes. And then you get on the platform where an int's 8 bytes, and now you're in trouble because your program broke. That happens in Fortran all the time, and so it's much easier to describe things in data types than it is in byte lengths. So for Open MPI, there's 2 parts of the data type engine. There's what I call the top part, which is the data type part, where you describe, okay, this is what my buffer looks like, and it has this many integers and this many floating point numbers in it, and then there's the bottom layer, the converter, which takes that description and gives the transport engine, all right, here's the IOVEC of base and bounds that you need to send. And maybe I packed it for you because this representation was so sparse that using IO vectors didn't make sense, so I just packed it for you. So we can ignore data types pretty much entirely. I'm going to spend a couple more slides on them, but you will probably never see those if you're just working at the device layer. Unfortunately, you can't ignore converters because they're part of the interface for moving bytes. And we'll talk about why a little bit later when we get to some of the nice diagrams of what happens when you send a message. So this table, not really important to this talk, but there's a whole lot of predefined data types. And like I said, they have C and Fortran data types. And from those, you can do user-defined data types, including things like, I want to send every 2 integers, skip an integer, or skip an integer, send 2 integers, skip an integer, send 2 integers. You can do descriptions like that, which is very useful if you're, say, taking a 3-dimensional structure and smashing it into the 1-dimensional memory array, and you just want to send one face. Or you can describe a data type that sends that sparse face, or another one that describes the face where you have nice long rows. And so with that, you can have data types that describe the memory. So instead of sending, having to pack all of the bytes out of the face into a nice buffer and sending that, you can say, I want to send this face data type, and here's the start of that face. And get a theoretically much more efficient way of sending messages. The converter, on the other hand, is all about moving just bytes, and its interface revolves around bytes and IOVEX, and it's what we as systems programmers like because we're comfortable with a base and a bound, right? And so it's based on 2 architectures, the local architecture and the remote. So a given converter only has meaning when sending from one process to another. If that same process is sending to a third process, it's a different converter, even if it's the exact same message. And the reason for this is there's an expectation among MPI programmers that even if I'm running on a heterogeneous architecture, where, say, I'm on an Opteron sending to a PowerPC machine where the endianness is different or the floating point representation is different, the MPI is going to take care of all the data conversion I need. And so The converter there then is different if I'm sending to an Opteron than if I'm sending to a PowerPC machine. So a converter, if you're programming to the BTL engine, the converters kind of have to be dealt with a little bit carefully, in that you have to know the right converter to use for a given endpoint, which is why converters were stored in these UMPI proc-T structures we talked about earlier. So you can either tell a converter, give me a big buffer that describes this entire data type that I need to send, or you can say, give me an IOVEC of all the little pieces. And which one you use largely depends on what you're trying to accomplish, but for the most part, the BTL interface itself only deals with a converter when it's give me big chunks that I can send using a DMA engine, which we'll talk about a little bit later, but this is one of those places where you shouldn't have to care about data types if all you're doing is moving bytes, but you do because of efficiencies. So creating a converter is costly. They're great once they're set up. And there's some more slides in the slide deck that we're just going to breeze through so we don't get too far behind. But the next place that we have to care about before we get to moving bytes is requests. So I said earlier that send and receive both have blocking and non-blocking variants. For the most part, inside of Open MPI, everything's a non-blocking variant. We take the blocking and make it non-blocking at some level. So at the device driver level, everything's a non-blocking operation. Why is that important? Well, you need to know when a request finishes. So at the top level, the way the user knows is when you call a non-blocking send, you get back what we call a request. Now, you get the same request object type back whether you were doing a point-to-point or a one-sided operation or a collective operation or an I/O operation. Don't worry about the Fortran bits here unless you like Fortran, but then there's a set of functions you can test. Is this request complete? You can also just wait until a request is complete. From a design standpoint, what you end up with is you have a base, kind of a class inheritance, and I apologize these colors didn't come out on the projector, but you have a base UMPI request T, and this is basically what the user sees. And this is what a test and a wait look at, some fields in here. The PML then has a base request that includes some things that are important for point-to-point messaging, like is this a send or is this a receive? And then there's individual stuff that each PML can add individually. So the OB1 PML, which is the point-to-point messaging layer for the BTLs, will have things like which BTL sent this message, whereas the CM PML, which is the one that uses those matching transport layers we talked about earlier that we said we're never going to talk about again, has a totally different structure because all it has is a pointer to the request handle that came back from the low-level device. And so it really doesn't have anything in there. And so that's how you get the abstractions nice. From the top level, all it needs is that UMPI request T has in there, is it done or not? And that's basically all test and wait need to look at. So this leads to these things, of course, like everything else in Open MPI for performance reasons are free listed, which means you get a lifespan that's cyclic because you're going to free it and then reinitialize it later. But essentially, all requests start out inactive. At some point, they become active because we've started them. At some point, they can either be canceled or freed, and then once they're cleaned up, they go back to inactive. So you have this nice life cycle that, again, not too important if you're at the BTL layer, but if you're looking at what the PML does and how it uses the BTLs, if you're looking at OB1, you'll see that an awful lot of OB1 has to do with making sure this life cycle stays valid, because if we end up with all of the requests either canceled or invalid when it goes time to create a new one, there won't be any in that free list. And we'll allocate more, and suddenly we have a memory leak. And there's applications that will create millions of requests a second, and so that memory leak ends up being real bad real fast. But again, from a device layer standpoint, you really don't have to look at these too often. So that's kind of the structures you need to have some idea about before we can start talking about devices. So now let's start talking about what actually happens when you move data. You start at the MPI layer. We're going to spend one slide here and then be done with it. It's located in the directory listed. It's basically all it does is it's where all the argument checking occurs. And then it makes a down call into the PML to actually start the data transfer. So this is a very thin layer. And as a matter of fact, there's a pound define to make it to turn off argument checking, and then it becomes a really, really thin layer. But this is what the user sees, and this is all the user cares about. But uninteresting for implementers or device driver people. So from a device standpoint, from a transfer engine standpoint, what you have is you have this thin MPI layer we talked about. Then you have the OB1 PML that we talked about, which is where we actually implement all of the MPI semantics. So this is where we ensure ordering. This is where we ensure that that all the matching occurs, where we deal with unexpected messages. All of that happens in this OB1 layer. Then there's a thin layer called the BML, and there's only one BML instance. And this is just a multiplexing layer. So beneath that are the actual byte transfer layers. And the reason this, which is usually a device, right? So there's different component types, and then each component type, say an OpenMP BTL, may have multiple instances that are created. So if I had, say, 2 InfiniBand cards, or as is common today, 2 TCP or 2 Ethernet ports, I would create 2 instances of the OpenIB BTL or 2 instances of the TCP BTL, 1 per port. This means I could have multiple BTLs that can talk to the same remote host. And what this BML layer does is basically ensure round-robin ordering or whatever ordering we want, although round-robin really works best for our applications between those BTLs, so that you can do message striping or load balancing across there. So we have a BTL. This is a code that actually moves data around. And it has a couple of different interfaces. It has I won't say a send receive, but it has an active message callback interface. So you call send, and the remote side makes an up call into the PML when message arrives. It also has an RDMA put get interface, and we'll have some diagrams of this as we go through it. It then depends on some pieces to help it along. So I don't know how many of you guys, how many people are going to be familiar with InfiniBand?
Not very many.
Okay. All right. So for TCP, these components don't really exist. TCP, we're stream-oriented, and all the buffering is handled by the kernel. We don't really worry about the DM pool and the R cache. But for networks like InfiniBand, which is a high-speed HPC network, there's no kernel copies involved. You talk directly to the device, the NIC itself, and in order to do that, you have to make some promises to both the kernel and the NIC. And one of them is that you'll tell it when you're going to use a section of memory for communication, either sending or receiving, ahead of time. And then the kernel makes the promise that it will tell the NIC that, and that it will not move that page, that virtual memory address, around in physical memory, because the NIC can't see the virtual to physical mappings that the processor can see. So it needs to be told what they are, and then it needs them not to change on it. And so this registration and deregistration of memory, as we call it, where you're making these promises, is kind of expensive. Actually, it's so expensive that it takes more time to say these 10 pages are going to be used for communication than it does on these high-speed networks to actually send those 10 pages. Which leads you immediately to, you have to reuse that registration, that pinning process. You have to send out of that buffer multiple times, right? If it's going to be more expensive to do that part than it is to send, and you want to hit that send speed, because that's why you bought this really expensive network. And so the M pool is exactly what it sounds like. It's a memory pool of memory that's been registered, that's been set up for communication. And so things like when you're sending a small message, you'll copy into memory out of the M pool and then send out of that. And we'll talk about some of the interfaces of that later. But that's kind of an important construct to a lot of the BTLs. The other important construct is a registration cache, which is exactly what it sounds like, a cache that you can quickly look up. Hey, is this address in the sections that I've already created a registration for? And we'll talk about those a little bit more as they become important in the diagrams through a send path. Yeah.
You said, if you go back to that last slide, you said something about the BML that I thought maybe you might want to say a little more about, and that is that it does round robin. So if I send 2 messages and I have 2 TCP modules, then the first message will go out to the first TCP module, and then the BML will direct the second message to the second TCP module?
Yes. All things being equal, which they usually are, yes. So I should point out that the PML enforces ordering. We'll talk about this a little bit more, but the BTLs, we try for performance reasons to keep ordering in a BTL, but we don't actually guarantee it. All the ordering reconstruction happens in the PML, and there's multiple reasons for that. One, we have this multiplexing point, and so you could take 2 paths and therefore end up out ordered. And 2, it makes the design of these BTLs a heck of a lot easier. The BTLs are reliable in both a given send will result in a receive callback occurring, and it will result in the right data getting there, but it doesn't guarantee ordering. And so, but yes, if you have multiple transport, if you have multiple BTLs from process A to process B, whether they both be the same type, TCP, or they both be different types, i.e. TCP and OpenIB, we will try and use both. Now, I said all things being equal, and this brings up a good point that probably you guys won't run into a lot, but people building test clusters, universities see this a lot, where they'll buy a bunch of different machines and stick them together and call it a cluster and hope for the best. If you have say an Ethernet card with, we assume TCP latencies just kind of hard-coded, and this is a bad assumption, but have, say, 100 microsecond latencies. And we can actually kind of pull the InfiniBand card to get an idea what its latencies are, but generally they're 2 microseconds. For eager messages, short messages, it probably doesn't make sense to send any of those across the TCP path if you have an InfiniBand path, because I can send so many more messages over the InfiniBand path in the same time that it takes to send one across the TCP path. And so there are cases where if things aren't equal, we will favor one over the other for certain types of messages. But when all things are equal, i.e. either the same transport path, same type of transport path, will round robin. So the PML, like we said, provides all of the point-to-point messaging semantics. So there's a whole bunch of different send types. These are totally unimportant because they all get smashed down to the same thing underneath. It guarantees message progression and the request notification and completion via the request objects that we just talked about. So it handles all of that. It has OB1, or the PML of choice these days, has 2 messaging protocols. basically an eager send. So for below a certain threshold, we're just going to cram all of the structure that we need to describe the message, the matching logic, right? The tag, the source, the communicator ID. We're going to pack that into the top of a buffer and then pack the data on and slam it over to the other side, and it's going to do something with that. And we'll talk about exactly how all that happens in a second. But that's the eager protocol. And we call it the eager protocol because I'm sending the data before I know that the other side's ready to receive it from an MPI standpoint. Now, the BTLs have to be ready to receive it as necessary from their standpoint, and we'll talk about what that means. But that's the eager protocol. The rendezvous protocol is exactly what it sounds like, in that you send a small message across saying, it's basically a request to send, clear to send protocol for those who used to do serial programming, programming over a serial port. But you say, I need to send you, in this case you say, I've got a 1 megabyte message that I need to send to you. Are you ready to receive it? And the receiver replies, yeah, sure, here's where to put it. And then the data gets, and then the sender actually sends it after it gets that clear to send. If you're sending big messages, remember, MPI messages can be sent, and the user doesn't have to actually give you where to sync that data. It doesn't have to give you the receive buffer right away. It has to eventually, but not when that data arrives. And so if you've got multiple 1 megabyte messages coming in, well, you probably don't have temporary buffer space to keep all of that. And so a request to send, clear to send protocol means that the sender keeps it in the user buffer where it already is, so it doesn't cost any buffering until the receiver says, okay, here's where I want you to put it. So we have those two protocols. They mean very different things for how a BTL transfers them, which we'll talk about. And obviously then the protocols are tuned for different types of interconnects, different types of BTLs, depending on what the BTL says it can do. So for some, like TCP, all it can do is a send-receive protocol. For others, like InfiniBand, it can do RDMA puts and RDMA gets, where I can just grab random chunks of memory from the sender. And therefore, the protocols for this rendezvous become very different, or hybrids of the two. And we'll go through all the use cases in the next couple of slides. So the PML interface is actually fairly heinously large, but a lot of it is unimportant for today and smashes down kind of into the same small set of calls. So there's a couple of calls to do resource discovery, basically. So when a new process is added to the system, added to the set of processes you know how to talk to. And MPI has a couple of ways of doing this. And I know Ralph has thought about some extensions for various ways to do this. This add procs call is called. And some guarantees are made in terms of what we call the modex, which we'll talk about as we go, about what data is and isn't available when this add procs call is called. But the short story of it is you have at this point, when add procs is called on a remote proc, the system knows enough to tell you how to contact that process at the very least, and probably a little bit more than that. There's an initialization call, a call that's whenever you want to make progress, some things to add more communicators, to add and delete communicators so you can add information for each communicator about its process set. And then there's the communication calls, and there's calls for receive and calls for send. And again, there's like 6 different receives and 6 different sends because MPI provides all of those, and there's optimization points. But really, you can view them all as a non-blocking send or a non-blocking receive and a wait in the worst case when it's blocking. So PML itself is located in the Topter UMPI PML. There's 2 of them today. There's Obi-Wan, which is really intended for software MPI matching. So all of the matching logic occurs in software. It does multi-device, so striping. It has an endpoint per device support, and it utilizes the BTLs for communication. This is the path we're most interested in. There's also the CM PML that's intended for offload matching. It's really single device, and it uses the MTLs. And this is really a special case for high-speed interconnects that were designed just to do MPI. And there's not many of those, and very few of them will be used in cloud computing for the foreseeable future, so they're probably not important. OB1 is found in Topter UMPI PML OB1, just like the naming convention that Jeff talked about this morning. So under the PML is the BML, which is the BTL management layer. There really isn't much to say here other than it's a very thin wrapper, and it kind of manages the peer discovery and then handles the round robining of BTLs. And that's basically all it does, is the round robining. And then the interesting part, the BTL, the byte transfer layer, it provides an abstraction around the underlying interconnect. It has a tagged-based communication interface similar to active messages. And what I mean by that is the sender explicitly calls send to send a message. The receiver, unlike say TCP or MPI, doesn't call receive, but instead the next time it enters the progress function, it makes a callback up to whatever upper layer wants to know about messages of type 5. And so I send type 5, and on the receiver, eventually a function gets called that says, hey, message of type 5 showed up. Here you go, and does something with that. So it also has facilities for RDMA, including setting up these memory registrations we talked about, and it supports both put and get and provides completion callback functions. So on the receive side, you get a callback function when the message arrived. On the send side, send is non-blocking, so you get a callback when the send completed. You also get a callback at any random time, whether you were doing communication or not, if an error is detected. For instance, a lot of networks, you get an error message, an error notification if your link to the switch fabric failed. You'll get a notification of that, and we'll pass up, hey, this BTL says it can no longer talk to anybody. What do you want to do? Now, granted, for MPI, the answer is usually, well, abort and figure it out later, but it does give the opportunity to figure out what to do when you can't communicate using that transport anymore. So the BTL interface looks a lot like the PML interface in some ways. There's the add procs and delete procs for setting up these endpoints. There's also a register function that is something that's common to active message type interfaces, where you say, this is where you say, as an upper layer, messages of tag 5, of type 5, I want this function called. And a PML or a one-sided interface, or whoever's using it, can have one or more callback functions. So the one-sided interface frequently has 2 callback functions because it wants 2 different types and it wants different things that occur with them. The OB1 PML only has 1 type right now. So everything that the PML does uses 1 type, and then it dispatches underneath. So we talked a little bit about registering memory and needing to send from registered memory on certain devices. The first place you see this in the BTL interface is that these send calls that we talked about, right, where I send a message and I get a callback on the remote side. You can't send from arbitrary user memory. You have to first get what we call a descriptor. And there's a number of ways to do that. The most common is you call BTL alloc, and it as the name implies, allocates a descriptor. You tell it, hey, I need to send 55 bytes. It gives you a descriptor at least big enough to hold 55 bytes. The truth is there's probably 4 or 5 different message sizes, and you'll get a buffer that size, but internally it can deal with it because it's all doing these memory pooling things, but it'll give you a descriptor big enough for that. When you're done sending it, you call free. If you want the opportunity to send directly from user memory, let's say you're TCP and you don't have registration, or you have a network that doesn't require this registration, you can call prepare source or prepare dest, depending on whether you're on the send side or the receiving side. And you can give it a user buffer saying, hey, I'm going to send this memory to this guy. And the prepare source function may pack all of that into a buffer and give you a descriptor back that's packed all this data. Or, more than likely, if it's a contiguous buffer, it will do all the important registration things underneath and give you a converter or a descriptor that describes, hey, this user said he wants to send from this data, we think, or this user memory, we think we can do this directly, so we're just going to give them a descriptor that describes the user buffer directly. The important thing in the interface is, and by and large, the upper layer protocol doesn't care whether it got packed or not. And then, of course, there's send, put, and get functions to actually move the data. Put and get do not cause data to move, but they don't actually cause any notification on the receive side or the target side in the case of a get. So there's local completion. So after a put completes, you'll get a notification, hey, put completed on the side that initiated the put, but the target won't find anything out about that. Same with get, right? You'll get a notification, hey, this get completed, the data is where you told me to put it. The target won't know that get ever occurred. And so the only way you can do target side notification is with the send, which dictates what a lot of our send protocols look like for big messages. Keep in mind, there's a maximum descriptor size you can allocate for that BTL alloc, which is the maximum you can send in a single call. Generally, it's somewhere in the 4 kilobyte range. So if you want to send 1 megabyte, you can either split it up into a bunch of sends, or you can use a send and a put, because the puts don't have much of a size maximum. So I talked about descriptors, the things you get back from BTL alloc or prepare source or prepare dest. There's a couple of different pieces to them. So basically a descriptor is a chain of segments, and a segment is a base and bound. And so you can have a source descriptor and a destination descriptor, and then you have some callback functions that get fired when there's completion. So this is where you register a callback function for whenever the send completes locally. But again, this looks a lot like IOVEX for people who have done TCP programming with IOVEX, except you have both a source and a destination. The reason for that goes back to this memory registration thing. If you think about it, the ability to randomly put data into some other process's memory space could, if done wrong, be one giant security hole, right? Hey, I can go modify this guy's code space. I can make it do whatever I want. This is great. Well, since it's not such a great idea, the way we usually deal with that is there's a 64 or 128-bit unique random number associated with each registration. That's a hardware level construct. And when you do the put, you pass the remote unique identifier that when it called register, it gave the user back that identifier. The user somehow sends it to the sending side, and the sender passes that along with the put call. So we need to pass these things around. These, what we call R keys, registration keys around. And the way you do that generally is on the you put the source, when you're creating the source descriptor for put, on the target side, you put the registration key as part of the descriptor. There's some nice functions for packing these descriptors around and passing them around that we won't go into in too much detail here, but they're fairly well documented and used in a couple of different places in the code. And send me an email or ask after we get through the slides if you want more details. In terms of what devices we have, so supported today we have OpenIB, which is Open Fabric's reliable connections. So this includes both the Mellanox InfiniBand cards and a lot of the RDMA over Ethernet cards. Self, which is send to self semantics, which is useful in that a lot of these interfaces, sending to yourself can actually be kind of problematic from a buffering standpoint. And so we have a BTL that does all of that. So if your BTL that you're writing doesn't deal with sending to self very well, if you're, say, doing a raw Ethernet device, and sending to yourself actually has some bad semantics in terms of what it's going to do to the NIC, well, just use a self BTL, and when when adprox is called on you, you say, oh, I don't send to myself. That's somebody else's problem. And we have a BTL that handles that. We also have shared memory that supports CUDA, the GPU programming interface, TCP, of course, a transport for the Cray supercomputers, and then there's a project out of SGI called XPMEM that allows you to cross-map regions of memory between processes on the same node. And we have a shared memory transport that supports machines with XPMEM support. This probably doesn't include anything that any of this audience is going to be interested in, but that's what the Vader BTL is. And then unsupported, there's a high-speed networking interface called MX, or MirrorNet, that had an interface called MX. We support that. The SCTP protocol, and then Windows verbs. And those exist in the Open MPI source tree, but really aren't supported today, either because they don't have maintainers who are actively supporting them, or because the hardware that they were used for has been retired. So we talked about memory pools a little bit. They really have a couple of functions exactly like you'd probably expect: allocate and deallocate. If you want to allocate something out of the memory pool or give it back. They also have a register and deregister, which is how you'd say, all right, the user gave me this buffer, so I don't need a new buffer, but I need to be able to send out of that. Although it's a little weird having a memory pool do that, that's kind of the design we ended up in, because we needed one place that knew all about registering memory with the hardware. And it was easier to do this than have it in two different places. So it's a little bit of a weird abstraction in that you don't think memory pools as dealing with user memory, but we do. And so we have register and deregister calls for when instead of getting new memory, you want to say, okay, the user gave me this memory and I want to send out of it. And the memory pool is used by a bunch of different components. The BTLs are the most obvious, right? Because they're the ones actually dealing with, can I send out of this memory or not? The PMLs also talk to the M pool to ask questions like, how close am I to my maximum amount of memory registered? Is it useful to try and use one of the protocols that's going to have lots of registered memory to get the message done, or should I just immediately fall back to one of the other protocols? And then the memory pool is also used by the MPI layer to deal with one call where the user can allocate memory that's explicitly for communication. And so all three things happen in one place. That bottom one really is of almost no impact to this discussion today. It's just an optimization point that the MPI interface has. And the registration cache then helps you find, all right, the PML registered this chunk of memory from point A to point B in the memory space. it has a registration key, and now I want to send that same buffer again, but I don't know it's the same buffer, I just know it's point A to point B. I need a way to quickly find out, one, is this memory registered, and two, what its R key is. And the R cache gives you that. It's a red-black tree. How it's implemented is fairly unimportant, but inside it's a red-black tree that you give it a base and bound, and it says, yes, this is registered, here's the real base and bound and the R key associated with it, or no, this isn't registered, go use the mpool to register it. And when the mpool registers it, it will automatically add that into the R cache. So the R cache is kind of a lookup interface for, is this registered? If all you're doing is short message send receive, you'll never really need to use the mpool or the R cache. So we're back to this slide, just so that now you can see how all the pieces fit together, right? You have where all the matching logic happens, you have your round-robining interface, and you have your device transports, which have their memory registration pieces associated with them and their red-black lookups. And this is actually not quite right in that we show the R caches in this slide as being per device. In reality, it's essentially shared across devices a little bit more cleanly than this, largely because in a lot of ways, we talked about you can have more than one OpenIB BTL. They share the same mpool and the same R cache, because when I register on one NIC, I'm actually going to register on all the NICs. And so a lot of that gets hidden underneath where you don't have to deal with some of those details, but there's a little bit more multiplexing going on than this diagram shows, but the diagram gets too complicated if you show everything exactly right. So now the interesting bits, what happens when I actually send a message? So for this example, we're going to assume we're using InfiniBand because it's one of the more complicated transport engines. It's one of the more featured transport engines. We'll talk about where there's all the code paths you'd use for TCP you will use for InfiniBand. There are code paths that InfiniBand has, the TCP doesn't, and I'll point those out when we get to them. But the OpenIB BTL, like I said, supports reliable connections. So this means that we know if we called InfiniBand send that we're going to get the message on the remote side. So we don't need a reliability layer in the BTLs. If we were, say, using UDP as our transport, the BTL would have to add a reliability protocol to say, it doesn't have to deliver messages in order, but if a message was sent, we have to make sure it's received. So the BTL is this reliability point in our stack. It has the ability to do send receives. So you call send, you call receive, and it says, okay, here's the message that was sent with what we call inline data, which is basically just an optimization that really small amounts of data can be sent really, really fast over InfiniBand. The other points are not important unless you're an InfiniBand expert, which I don't think we have here, so we'll skip over. But the one thing to say about the send-receive protocol is InfiniBand send-receive protocol, the send fails if there's not a pre-posted buffer on the receive side to receive the message. So unlike MPI or TCP, where when I call send, the message just gets buffered magically somewhere until the receive is called. With InfiniBand, you actually have a split transaction in a lot of ways. You say, here's some receive buffers. And then later on, you say, I want to receive a message. And it gives you the first message that's been delivered into one of those receive buffers. This makes life a little bit complicated in that for the InfiniBand device, for the InfiniBand BTL designer, in that we have to figure out how many messages to keep pre-posted. Because we can't send a message and not have a receive buffer on the remote side. And so this is where complications can incur if you're writing a new device driver. right? If you're doing a raw Ethernet device driver, the same thing applies, right? If there's not a receive buffer when the message comes in, the message is gone. And it's up to you to figure out what happened. InfiniBand gives you some nice notifications. Hey, the remote side didn't have any receive buffers, and I didn't know what to do, so recover for me. Whereas raw Ethernet probably won't even tell you that. So first thing, we start up, right? We're a brand new process. We don't know how to talk to anybody. First question we have, which PML are we using? This is a really bad heuristic right now, and we're just going to ignore this and say we chose Obi-Wan, right? So we're using BTLs. We want to use InfiniBand, so we chose Obi-Wan, and now we initialize the BTLs. The InfiniBand, the OpenIB BTL said, hey, I see an InfiniBand driver, or an InfiniBand card, and it looks like my endpoint ID is blah, blah, blah. And it tells a system that we call the modex, hey, I've got an InfiniBand card and it's got endpoint ID, blah, blah, blah. And the modex is a scalable data share. It's basically a key value store, for lack of a better term, where an individual endpoint says, here's some information associated with the OpenIB BTL or the TCP BTL, and only the BTL actually knows what the value part means. But we have a fairly scalable all-to-all algorithm for sharing this during startup. So we've shared all this information now, and MPI init has built this giant UMPI proc-T array that we talked about, and created all the processes, filled in their architecture types, and the PML has had add procs called on it for all of those, and it goes into an individual BTL and says, hey, for process 5, can you talk to it? And process 5 says, or process 1, let's say process 0 says, gets told about process 5. Process 5, 0 then goes and asks the modex, hey, do you have an OpenIB BTL endpoint information for process 5? And the modex goes, sure, here it is. Now, that doesn't mean you can talk to it, right? Because if this was TCP, it's possible to have two disparate networks and you can't talk to each other. With OpenIB, the same thing can happen. You can have two InfiniBand networks that maybe aren't connected. And so you do some magic to figure out whether you can talk to this remote peer or not. In InfiniBand, there's very nice functions to do this. So it's very easy. You call a function saying, hey, can I talk to this endpoint? And InfiniBand card says, sure, why not? So I tell the PML, yeah, this BTL, this OpenIB BTL can talk to that endpoint. And the PML and the BML then say, okay, great. I've got two endpoints, from rank 0 to rank 1. I've got two BTLs or one BTL that can be used to talk to that remote peer. And as part of that, while I'm saying, yeah, sure, I can talk to that, I say, yeah, sure, I can talk to that. And when you want to talk to it, here's an opaque endpoint structure pointer that I want you to pass back to me every time that you talk to it. Right? So this is one of those places where we want to do some caching to make where caching kind of becomes important. If you think about how you might do this if you say didn't have a connected protocol, what you'd probably have is a process name came in and I do some kind of log-n lookup to get to the right pointer. Because I started with a communicator, I can chase down very quickly through two pointer chases to this endpoint ID. And so I can have direct cache lookups instead of trying to do a log-n algorithm. And yeah, it's a couple of cache misses probably because you're chaining through these structures, but that's still better than anything log-n, right? So that's why you pass up, okay, for this process, I want I want you to pass this endpoint information, this opaque structure back to me, is what we're trying to do is get any log-n or linear lookups out of the critical path and go just for, store all the cached information right next to each other in an easy to look up way for the upper level without exposing all of these connected process semantics down to the BTLs. And so the BML sorts BTLs into 3 buckets. Those that can do eager messages, which should be all BTLs, right? Those that can have a send-receive interface. That should be all BTLs fall in that category. It then, that's the send category. It then goes and sorts those by, it sorts those by a reported latency parameter that the BTL reported when it was initialized. And only those with the lowest latency parameter get put in the eager list, which are things that are used for low latency small messages. And then there's the ones that can do RDMA for big data transfers. So for the most part, we only use 2 of these lists, the eager list and the RDMA list. The send list, we just don't fall into a case where that's important very often. So OpenIB discovery, we kind of went through already how that all occurs. And you end up with this mess of a data structure. So off the end of an UMPI proc T, a given UMPI proc T, sits a BML base endpoint. Off of that is a back pointer for various reasons, the list of eager BTLs that can send to that process, the list of send BTLs and RDMA processes. Associated with each entry in this list is this BML BTL structure that includes the function pointers and a module pointer, which gives you which is the module interface that Jeff would have talked about this morning for talking to a given component instance, as well as for each instance of a component, there's the endpoint that was passed back up. And off of that, OpenIB stores a bunch of things like the remote GUID, the remote ports, how many ports there were, and then it also has queue-pair information, which is a queue-pair is like a socket in TCP. It's a connection across which you can send data. And so, again, it's fairly quick. There's no log-n lookups. It's just direct array indexing to get down to an endpoint from a communicator. And so TCP has a fairly simple, in the TCP case, this is basically a socket pointer or a socket. That's a much simpler infrastructure if you're doing something like TCP. Although we are pretty consistent to keep the names the same across all of these. The structure, while you might not have some of these structures that may not be as complicated in the TCP case, the names are going to be fairly similar. Take out OpenIB, put in TCP, and you can kind of know what that structure is being used for. So if you're writing a new BTL, you want to try and keep the names the same just because someone else coming along to read it, to fix a bug, or to understand a performance metric is going to expect the names to be fairly similar to what that list had. So send. We want to call send. We want to call MPI send. We start with the MPI call. We did parameter validation. We ignore that. We then call into the PML. The PML basically doesn't do parameter validation because it's already been done. We don't, in the PML interface, reduce it to the base case of a non-blocking send for performance reasons, none of which have anything to do with the OB1 PML. This has to do with the other case, the CM. And we'll start with a blocking send call entering OB1. So we've called MPI send. It's called into OB1. And the first thing we do is allocate a request. Is allocate a send request. This pops off a free list. We fill in information we need, like what's the tag, where am I sending it to, what converter do I use to pack and unpack data, and then we start the send request. So from the OB1 PML level, everything's non-blocking. So the idea is, you enter, you do as much as you can locally, and as soon as you have to talk to a remote host or do a long-lived operation, you return control to the upper layer. The upper layer may stay in the PML in the case of a send call, in that the PML send is just going to call a non-blocking send followed by wait. So you may not actually get out of the PML when I say return another upper layer, but the idea is a given function never sits there and spins waiting for remote data, that you always return up in the stack and try and progress a whole bunch of things at once. So we've initialized a request. It's basically filling in a bunch of structures or a structure off a free list. There's a nice macro for doing it. Not unexpectedly called OB1 send request init. We are very long-winded in our function names. The good things is, in general, they're fairly self-explanatory function names. So we want to request start a request. The first thing we do is ask the BML what BTL I should use. So I'm going to, let's say this is an eager send, it's a short send. So I'm going to look at the eager list. I'm going to get the endpoint information for the, or I'm going to get the BML endpoint. I'm going to ask what's the first BTL in your eager list. It's going to tell me and bump the counter to the next in the round-robin fashion. And that's going to give me both the BTL module and the BTL endpoint for talking to that remote peer. And now I'm going to schedule the communication call. There's a function, OB1 send request start copy. As the name implies, it's going to do a copy and then send. So how is it going to do that? Well, first thing it's going to do is call BTL alloc to get a descriptor. This is a descriptor we can send from. We told it our eager limit. How much we told it its message size. It said, sure, here's a descriptor. The OB1 then, and this may do a whole bunch. This is all free listed and may grow some free lists internally in the BTL using the mpool if necessary. The converter OB1 then packs the data into this send descriptor using the converter that was created in the previous step. And the header information is populated with the tag value. And then the BTL send is called with that descriptor and the PML callback function. Now, before we send that descriptor, one of the things we've done is set the callback function for what function should be called when we get local send completion. We then call send. On sender side, when we get send completion, since it's an eager message, we know we won't need the user's buffer anymore, and so we mark the request as complete. And when the callback into the PML for send completion occurs. And that's all the PML does. It's a pretty short path for an eager message. For the BTL, let's say BTL send was called. We get if we're using OpenIB, we've got some work to do. If this was the first send, we're talking to a remote peer. Your average job size, well, let me rephrase that. Job sizes can get quite large, 10 to 30,000 endpoints. Wiring up a socket or an InfiniBand queue pair for each peer at the beginning of time is going to result in a lot of resources being used by the system that the MPI user is never going to need. Most MPI applications only talk to, say, 10%, 20% of their peers. So eagerly setting up a connection to all of your peers is going to be really expensive and a total waste. So what we do is what we call lazy connecting. That is, we only establish a connection, a communication channel between two peers when we actually send to it the first time. And so if this is the first time I'm going to send, in the endpoint data, I have a flag somewhere that says whether I've set up a connection or not, or TCP, I initialize the socket to -1 and look, is it still -1? Yes, then go through a connection protocol. And so you'll see this a lot in BTLs because there's this resource usage limitation for large-scale MPI jobs. Where this might affect you if you're using the BTL is that the first time you send a message to a remote peer, it's going to take a lot longer than the second time you send a message to a remote peer. And so if you're kind of latency constrained, if you know, okay, process A to process B is going to be latency constrained, and I don't want to take that hit in the first time I happen to send to it, during initialization, you need to account for that and send a message and do a ping pong protocol or something like that, because the BTL isn't going to have that channel created until you need it. And so you may need to force needing it early. So I said before, BTL sends reliable but unordered. And so that gives you a whole lot of optimization opportunities, particularly if you have to give your own reliability protocol, in that it's frequently going to be better to, let's say you dropped a message because you're doing a user level reliability protocol. It's frequently better to keep on popping up completion messages even though it's out of order, and when that retransmit comes and you finally get the missing packet, then pop that up. As someone using these devices, this is a royal pain in the butt. Because what it means is that you have to have, if you depend on ordering as an upper layer protocol, you have to maintain that ordering yourself. So Obi-Wan has a list of sequence numbers from every peer, and it starts at 0 and works its way up, right? And it will queue messages that arrived out of order to maintain ordering. Why this is a pain in the butt? Well, the one-sided interface has to do the exact same thing because it has ordering constraints. So if you don't have ordering constraints, not a problem at all. But if you do, this can be kind of a pain in the butt. So that's it. We've gotten to the bottom. We've sent the message, right? Once you get to BTL send, the rest is actually pretty easy. It's you've got a nice packed buffer. You know how to call send. If we're using TCP, message flies over the wire using magic, however we want to do it, and arrives on the other side. The other side, we're going to start. The receive side is always kind of hard to describe because two things are happening, and their order is kind of random, right? There's the message arriving, and there's the user posting an MPI receive, and sometimes the receive gets posted first, and sometimes the message arrives. So we're going to start describing the path from the MPI standpoint, from the user standpoint. So the user calls MPI receive. That calls into the PML. This should all sound vaguely familiar from the send case. A receive request is created. It's initialized, and then it gets a little different. So we don't actually have anything to do necessarily now, right? Because we're the passive side of this communication, right? The send side is kind of active, right? Something happens when you call send. So the first place that this gets a little different is the converter, remember, is endpoint specific. Well, because we have this any source we can receive from anybody, we don't actually know what the endpoint is yet, so we can't initialize the converter. So there's the first difference. Again, not important as a BTL user, but or BTL writer. And then we start the receive request. First thing it does is look through what we call the unexpected list, which is fragments that have arrived that haven't matched yet, that haven't matched to receive yet. And if one of those matches, then we know, okay, this is a fragment that came in, a header that came in, and we're going to continue on the message. If it's not found, then we put it on what we call the expected list, which is the list that an incoming fragment will search to see if there's a posted received that it should continue on. So when a fragment comes in, the progress function that we talked about earlier will be calling, TCP's receive function or get a completion queue entry from InfiniBand. And there's some magic as to how this happens through the BML that's really not important. But a message comes in, the BTL figures out what active message callback to call, and calls that function with a pointer to the buffer that was sent. Right, so that's pretty easy. A little bit of work there, but fairly straightforward on how to do that for most networks. And then things get interesting. We're back in the PML layer, or the one-sided layer, in this case the PML layer. Recall that at the beginning of time we registered this function that's the PML function. There's one callback for OB1. It's this receive frag callback. And then it gets dispatched from there to the particular type of send transaction. But basically, in the end, what you're doing is searching that expected list to see if there was a match. And by match, I mean that it was the right tag, the right communicator, and the right source for what the message that came over the wire. If there was, we call the matching engine and the completion engine and do a whole bunch of data things we'll talk about. If it wasn't, it gets put in the unexpected list until a matching receive is posted. And then we do all the magic that we're all about to talk about with unpacking. So we assume that we've gotten to the point where the message was matched. It doesn't matter which code path it came through, whether the receive got posted first or the fragment, or the fragment arrived first. It doesn't matter which. We end up, it's time to unpack the message. With the we now initialize the converter. We know what the source was, so we can initialize the converter. We're under the eager limit because we said this was a small message. So we use the converter's unpack function to copy this into the user data. We mark the request as complete, return the request back to the free list, and we're done. One thing that's worth noting, because it trips people up, the BTL descriptor that's passed to you in an active message callback is only valid for the length of time that the caller is in that callback function. Sorry, the callee is in that callback function. So if the callee, if the PML in this case needs to buffer that data, say because it was an unexpected message and it has to put the data somewhere, it is up to that layer, that in this case OB1, it is up to OB1 to buffer that data on its own. It has to copy it out of the descriptor. That descriptor, as soon as you return from that function, that descriptor is no longer valid. In practice, this causes some extra copies for the MPI layer, but for other protocols doesn't tend to cause problems, because normally, for instance, for a runtime environment, you tend to get the callback, act on it, and are done with it. Right? So if the callback is saying, hey, I need you to update this database entry, if you have, if you're building the modex of this global database, the message arrives, you update the database entry, you don't need that data in the descriptor anymore. But it is important to note that you cannot hold on to that descriptor for a long period of time. Now on the send side, a descriptor is valid until you explicitly get rid of it, and by calling free. And when you call prepare source or prepare dest for the RDMA transfers, the descriptors are alive until you explicitly delete them. The callback functions are the only place where they have this limited lifespan. So short messages, did that kind of, I know it's fast, but did that kind of make sense to everybody? What happens, you blow through, go down. Long messages, we talked about, use a request to send, clear to send protocol. A whole bunch of protocols we'll go through as to how to do that. The easiest one is an RDMA put. So the sender sends across the match information using BTL send. The receiver calls prepare dest, eventually matches, calls prepare dest to prepare the receive side buffer for receiving an RDMA put operation. And then there's a BTL send to send an ACK with all the match data that came from the R key that came from this prepare dest. You then call prepare source. These are BTL functions we're calling into that prepares the send side for transferring data, for doing an RDMA put. And then we do a big RDMA put. And when we get local completion of that, because keep in mind for a put, there is no remote completion for a BTL put, we send what we call an RDMA fin at the OB1 layer, but we do another BTL send to send across a finished message, and then the receive can be completed when this arrives. So from a BTL standpoint, we did a BTL send, a prepare dest, a prepare source, a prepare dest, a BTL send, a prepare source, a BTL send, or a BTL put, another BTL send, and then we could free all of the resources. Now, when we called prepare source, these probably underneath called a mpool register or an rcache lookup to look things up. And so these might have been very fast operations as prepare source. But as you can see, there's a lot of sending messages back and forth. Why is this at all the right way to do this? Well, on many networks, TCP not being one of them, this RDMA write, this put, is much, much higher bandwidth than those individual little sends. Because one, I can send megabytes at a time. And two, I don't have to talk across the PCIe bus sending commands and waiting for commands to complete nearly as often. So from an MPI standpoint, I want to send these as often, I want to use this put as often as I can. Now, there are times, like the one-sided I talked about earlier, where I know what the receive is going to be all the time, and then the code path looks a little different. And this might be applicable to frequently is applicable to runtimes as well. Then I call this prepare dest at the beginning of time. I send the R key across at the beginning of time. And then I call prepare source if I need it or not, but I already know this part, so I can skip this and maybe this and just do the puts, right? That I can skip huge chunks of the code path if I already know the destination virtual address. That really and know that it's prepared. That really this reuse that you get in MPI is just because you don't know you're not sending to a virtual address, you're sending to a tagged queue. And it's a tagged queue that's shared between all the processes, so you don't know you're going to hit the same virtual pointer every time. There were a lot of messages in that protocol. Well, if you have an RDMA get, we can actually get rid of some of these. And now we prepare source, send the R keys across with our match header using BTL send. When the match occurs, we call prepare dest and issue a BTL get, which under the covers is sending a rendezvous request, but we don't see this part happening. This is all asynchronous. And then we send a BTL send to send the completion to the send side, so we can mark receive completion here and send completion here. And again, we have to do this part because put and get don't give remote completion in the BTL interface. Only sends have remote completion. And so those are kind of the two, those are the two simple long message protocols. Now I said earlier that prepared source and prepared dest can actually have a fairly long latency event, right? That calling those functions may actually take longer than it would take to send the data. And so we have another protocol that the PML uses called the pipelined protocol. And what we do is break this big message up into a whole lot of small messages. And we start with some eager data that we're going to send through the BTL send interface, which doesn't have, that's using these pre-registered memory pools that we created at the beginning of time, and therefore are fairly quick to maybe a little lower peak bandwidth, but we can get them started really fast. And then we're going to use a whole bunch of little puts or gets, medium-sized puts and gets, I should say, where we're going to prepare source and then send, and we're going to try and set the pipeline up so that what we actually get is, and I'm going to give the punchline and then come back. What we're trying to do is set it up so that we start the transfer, and then we're pipelining the preparing the memory, doing this registration with the actual puts, so that you get everything kind of slammed together, and so you don't have this really long period of time where all you're doing is preparing, where all you're doing is the NIC and kernel registration, and then you're sending, and then you're freeing, that you're doing a little bit of both at the same time, because the NIC is perfectly capable of sending while it's preparing a different buffer for sending. And so what this leads to, the way this works, first thing we do, of course, is send the request to send, because on a long message, that's always the first thing we do. When we get the match back, that's a BTL send. We do a couple of BTL sends that instead of sending just a little bit of data, we send whatever the BTL tells us is the maximum amount of data we can send. And that's one of the options in the BTL structure that you get is, what can you send very low latency, and what's the biggest message you can send using your BTL send protocol. And so that's just priming the pump. And while we were doing those BTL sends, while we're copying, we're going to start priming the registration pump. And basically, what's going to happen is on the receive side, as soon as it sends the match ACK, it's going to start calling prepare dest on the first of those RDMA fragments. As soon as that's done, it's going to send a ready message, a clear to send message for the put for just that part. And then it's going to start registering the second part and the third part and so on. And as soon as it's done registering its chunk of memory, it's going to send a callback. And so this is we're trying to, we use those sends to prime the pump while that first thing was happening. And now as soon as we get a clear to send, we're going to call a prepare source and a put and a BTL put. Prepare source, BTL put, right? As soon as we get an ACK, we're calling that. So the receive side is pinning memory as fast as it can and sending ACKs as fast as it can. The send side is completely event driven. As soon as it gets a callback with a clear to send for a put, it calls prepare source and send. And then it doesn't do anything until it gets the next prepare source, clear to send piece. And so that's how you end up with this big, nasty, probably unreadable if you're watching the video in case we inserted the slide. But again, what's important here is that it's all of the pieces we were showing before, where it's this clear to send smashed together. And this only works if we got the timing just right. And so you're going to see some really weird sizes frequently for your eager send size and your max send size and your RDMA pipeline send size. And the reason is each network is going to have, based on how long it takes to register memory versus your bandwidth, you're going to want to tune those parameters differently to get this nice pipelined large message transfer. Now, this is the protocol that we use when we don't know that the send and receiver are pre-pinned, where the send buffer and the receive buffer aren't actually in the registration cache. Once they're in the registration cache, because we've run this protocol on that buffer, if you were to reuse those buffers at the PML level, the next time we're going to use those really simple ones that I showed before this pipeline protocol, where all you do is one big put. Why? Because the prepare source time is now a red black tree lookup, and it tells you, oh, look, here's the registration. So we don't need to do all this nice pipelining protocol with, this has a lot more messages we're sending, a lot more overhead than a simple put protocol. But it has the advantage of we can pipeline a lot of things that are very serial in the simple protocol. And so this is why we want registration caching. The registration caching is a little bit tricky because buffers can be freed and reused from a given virtual address you can call free and then call malloc again, and it might have a different physical address behind it. The good news is that we have some linker tricks, and the rcache is hooked into these linker tricks so that we see that memory is being freed and being reallocated, and we'll clear out the registration cache. So if the user calls malloc, does a send of a long message, calls free, calls malloc again, does a send. Right? Even if the virtual address was the same between the free and malloc, that doesn't mean the physical is the same, and it means the registration cache almost certainly got invalidated along there, or the registration to the NIC. We will clear out the cache underneath without you doing anything. So from a BTL writer standpoint or a PML writer standpoint, you don't have to do anything. Now, how do we choose which protocol we're using? This is the tricky bit. This is where the abstractions kind of break down. So I said earlier that the PML uses the mpools and the rcache. And there's really, in the simple model, if you're looking at it when we first designed this, there was no reason for that to be true. However, the PML is the one that decides whether we run this heinous mess or we run the simple single put protocol. And it's the one who decides whether it calls prepare source on just the little chunk for the pipeline or the whole big memory. And the way it does that is it looks in the registration cache. It peeks in the little registration cache on the side and says, hey, is this registered yet? And if the answer is yes or no, it chooses either the single put or the pipeline protocol. And so if you're writing a protocol that's trying to get high bandwidth out of arbitrary user buffers that uses the BTLs, you too have to sneak into the registration cache and use its one function, right? The component basically has an insert and a lookup function, so it's really easy to use, and find out, is this memory region I want to send in the cache or not? And if it is, then you can call prepare source and know it's going to be fast. If it's not, then when you call prepare source, you have to be prepared for the fact that that could be slow. Again, so prepare source and prepare dest, one of the problems with them is they're one of the few functions in Open MPI that are both slow and blocking. And so some care has to be taken there, as it can really screw up your timing if you're not prepared for that. alloc is always going to be pretty fast, but prepare source and prepare dest can have some problems. So since I'm running out of time, that's the communication protocol. Some future plans that will impact writing to the BTLs that are worth mentioning. BTL relocation, fault tolerance, and threads, and we'll talk about all three of them. The first, today the BTLs live in the Open MPI, in the MPI layer. Jeff talked about earlier, there's the Opal, there's the Orte, and there's the UMPI layers. Opal being kind of single process, no concept of a parallel job, portable abstractions that are useful for MPI. Orte being where we introduce the concept of a job, of a runtime, of multiple processes that are in some way related. And then the UMPI layer being where we implement the MPI semantics. So we want to take the BTLs from where we implement the MPI semantics all the way down to this portable process layer. Now, the first problem we run, the reason we're doing this is multifaceted. The first being the runtime really wants to use high-speed interconnects. When we first wrote Open MPI, we envisioned the runtime being something that started processes, got out of the way, and eventually killed the processes. We're now doing more and more with the runtime, and Greenplum is trying to push that even further, right? And having a high-speed interface would be really, really useful. The second reason is we want people outside of the Open MPI project want to use them, but they don't necessarily want the concept of a portable job or of the job layer, of the Orte layer. One of the places that this would be useful, I mentioned earlier, Portals 4 from Sandia. We have a reference implementation. We had to rewrite a lot of the InfiniBand code that we would have just used the BTL interface. But being a network abstraction layer, we don't want to bring in the concept of a job because not many TCP doesn't or InfiniBand doesn't have a concept of a job, and neither does the Portals interface. We don't want to introduce one, but we still would like to use all the communication stuff. And so we want to move the BTLs down. There's some challenges in here that are ongoing. The primary one is the modex. So I talked about earlier, there's this magic key store database, and it's been architected to be very fast so that everyone can put in their endpoint information and then get out their their friends' endpoint information during ad procs. That all relies on having a concept of a job, of having a concept of related processes. Well, I just said we wanted to get rid of that concept. So we need to come up with an abstraction that when we're in a mode where we have the concept of a parallel job, i.e. at the MPI layer, that we can very quickly do that key store sharing, but in a very scalable all-to-all way. But when we're doing something like, say, bootstrapping, when we're using during launch, for example, where we don't have a global consensus yet because we're just bringing up all of the runtime, where we can do possibly a less scalable but more flexible initialization of who your friends and family are, who the related endpoints are. And so this is kind of a challenge for us because we haven't found an interface yet that really works, but I expect we will in the next couple of weeks as we start moving code and experimenting. The other place is endpoint caching. I talked about we have this really nice flow down. There's one place the endpoints get stored, and you can get there without any log-n lookups, and it's just all straight easy indexing. That's going to be a little bit more difficult when we have more consumers of the interface, some of which don't have the concept of who I'm connected with. Because again, this will be used during bootstrapping. So that's going to be, just kind of looking at code and as we start moving things. And so I'm bringing this up as a challenge because it is. The big place it's a challenge is we don't know the answer, and so I'm giving a talk on how to use something that's about to change. And so that's one of the places where change is inevitable, that the BTL interface itself is going to probably remain the same because that's worked very well for us, but how you get that endpoint information is going to be different. And then the final part is the way we handle, I talked about there's a tag for which callback to fire. And the way we do that today is there's a header file in UMPI MCA BTL types.h, I believe it is, the header file, that has a bunch of constants, and when you want to ascend type, you put a #define in, and you claim it as yours, right? The one-sided's claimed a couple, the PML has claimed one, the collectives have claimed one, and you just keep adding them in. That works great when you're at one layer and there's not a whole lot of sharing going on, and you're at the top of the stack, so you don't have to worry about, well, is the MPI being used next to, Greenplum's, runtime, next to the Portals 4 device stuff, right? But all of whom may have had slightly different, builds of, which they're linking against the same opal, but the opal was built first and then everything comes next. That doesn't really lend itself to a #define in a header file very much because they probably didn't share a header file. The other difficulty is for performance reasons, we want everybody to have the same, the PML index should be 5, for example, or whatever the number is, across all of its processes. What you don't want is to have to look up the endpoint tag for your communication device. because that's more linear, big O end state that you have to share. Right? It's more big arrays that you have to have in your process. So we don't want to go that route. And so there's some difficulties there that we're still sorting out. There's a number of places looking at this. Sandia is interested in this. Greenplum's interested in this. University of Tennessee is interested in this. So this is going to happen. It's just a matter of when. The other is fault tolerance. You guys have probably been worrying about this a lot longer than HPC. HPC doesn't tend to worry about our fault tolerance issues are very hard to solve and very different than, say, a MapReduce world. And so there's a couple of ways we're looking at this in Open MPI. For the most part, our concept with fault tolerance is that a BTL, at the very least, just needs to declare when it can no longer send messages to a remote process and give that notification back. That's pretty much consensus that we should be able to do that. What happens next is where we have some very differing opinions, and I'm sure what Greenplum is interested in is going to be very, very different than, say, what the MPI level is interested in, because our fault tolerance issues are very different. But essentially, there's a PML that handles BTL failover for some of the BTLs that can report, hey, I can't talk to this remote process anymore. And so it takes striping and reduces it, the amount of striping you can do down across the job. That was the BFO PML. It's no longer maintained because it was written by Sun before it became Oracle. There's checkpoint restart, either system level or app assisted. There's run-through failure that University of Tennessee is working on. And for the most part, BTLs aren't impacted by any of this research other than we need to return errors properly on failure. We shouldn't abort. We need to be careful what we print. And we probably need to add timeouts in a lot of these places if, say, if errors are just treated by silently dropping messages, right? Because a lot of interfaces won't tell you anything useful if the remote side isn't there, but tell you that will give you an acknowledgement that the remote side receives a message. And so there's some things there that a BTL might need to do. We're still working on cleaning up a lot of the BTLs. So if you want to do fault tolerance, talking to the developers mailing list is probably worth it to figure out which BTLs are in which state. But the idea is they're going to return clean errors, and then the upper layer is going to deal with them as it sees appropriate, because as it sees appropriate is very different from one upper layer to the other. And then the final thing is threads. There's two ways to look at threads if you're a BTL consumer. The first is the BTL thread safe? That is, or thread hot? That is, can I make multiple calls? Can different threads simultaneously make calls into the same BTL? Today, the answer is maybe. How's that for a reassuring answer? It depends on the BTL. Some BTLs are finished with their thread safety over, they've been made thread safety clean, for lack of a better word. The TCP BTL and the shared memory BTL are two of the ones that you can make multiple calls from different threads simultaneously into the same BTL and nothing bad happens. OpenIB is a disaster right now in terms of this, and this is ongoing work. We're trying to clean this up, but right now the InfiniBand stack, bad things happen if two threads call BTL send at the same time on the same BTL. So we're getting better on that. That's active work. My guess is by the end of the year we'll be much better than we are today. The other way to look at it is today I talked about the progress, those completion callbacks, either local completion or, hey, a message arrived. Only fire when you call UMPI progress, or that OPAL progress function, right? So the upper layer calls down saying, hey, I need stuff to happen. The BTL calls back and says, yep, here's what happened, right? That's great, except if you have an environment where what you really want is asynchronous response to incoming messages, well, we don't have that because you have to sit there and actively poll. This is something we're actively working on, but it's really complicated because MPI is very concerned about message rate and latency. And there's some impacts there that we'll talk about in a couple of slides. So in terms of what happens with threads, places that you have to be careful with threads if you're looking at PML code, the requests have one giant lock around them. And so when you want to complete a request, you have to get the lock, modify the request, release the lock. This is largely so that we can do condition variables and block threads that are calling MPI wait on a request. So PML, there's not a lot of places that you have to do locking. Free lists are all thread safe by default, which is most of what the PML is doing. The one place is the unexpected list and the expected list. This is one of those places where it's truly awful. MPI matching is truly awful because no one's figured out a better way to do it than have a lock for both requests. There's no lock-free list searching here because there's all kinds of ordering constraints that are kind of hard to match. And so for the most part, those have a lock around each one of them you have to grab. BTL locking, it's all up to the BTL, right? The idea is the BTL does whatever it needs to support the thread safety and asynchronous progress. If you're using TCP, this might be kind of complicated because you have a stream interface and you really don't want to intermix streams, right? You're probably calling send, looping over the send system call and to send a single message and as a stream, and you probably don't want to interleave those things. So that can be kind of complicated. If you were doing something over UDP where your max send size was a single UDP fragment, that probably gets a lot easier because you don't have to worry about keeping the stream because nothing's ordered at a BTL level. And so, a system call then gives you the atomicity you need. And again, free lists are, which you'll probably be using a lot of, are already thread safe. So how complicated the BTL is largely depends on how complicated the underlying device is. Now, the one place that I was talking about that we're still research in progress is how to handle asynchronous progress. So our original plan, way back 5-6 years ago when we thought about this, was that each BTL would launch its own progress thread. And when it launched a progress thread, all progress would come from that progress thread. Now, this led to an inevitably awful design choice. That basically, so theoretically, there's no difference between callbacks from whether they're coming from the BTL progress function or from a progress thread. The PML is supposed to be thread safe, so it shouldn't care. And so this just gets us to the problem. MPI cares about latency, gap, and message rate. For those who have taken a networking class, you know that these are all basically the same thing. The progress thread, if it's blocking, increases latency significantly. In that you have to wait, it's blocking on something, that probably means the system has put that thread to sleep. Waking that thread up inevitably takes some time because it takes trapping into the kernel. When you're trying to get 1 microsecond end-to-end latency, you can't trap into the kernel, so you've taken a latency hit. The other way is to have that progress thread hard pull on whatever completion queue device you happen to have. If you're doing, InfiniBand, there's a completion queue entry get call. This generally hurts your message rate This generally doesn't hurt your message rate unless you've oversubscribed the cores because you said, oh, I've got 8 cores and I'm going to run 8 MPI tasks. Each launch the thread that's trying to do MPI communication as well as this progress thread. They're all banging away. You're overscheduled. And so now you're flip-flopping between the thing that can actually complete a message and the thing that is calling MPI receive to start the message reception. And that drastically increased your latency because you can't complete things except when that time slice occurs. So one of the things that we've started looking at that I think holds some progress is the model that MPI-CH uses, where essentially you have different conduits, for lack of a better word. We would probably use either BTL endpoints or specific tags or options, where you would set a flag that says, this is an eager message, which would mean I don't need asynchronous progress on the remote side, but I need really low latency. And then another one that would say that, and another flag that would say that this is a long message, meaning, or this is a message that requires asynchronous progress. And so the user of the BTL then would make the choice, do I want really low latency or do I want asynchronous progress? And that way you could have 2 channels. Let's say you were InfiniBand again. The one queue pair, the one channel that was low latency would get checked every time that there was that you would enter the progress function, and the one that gave you asynchronous progress would put you to sleep, wouldn't get checked as often, but could be checked while you weren't actively in the MPI library because it's all asynchronous with the thread. And so that way the thread can fall asleep, can be put to sleep without impacting latency of short messages. And so that's probably what we're going to go to, which again makes the upper layer more complicated, but also probably gives you the performance trade-offs that you're looking for. And so that's kind of it for the future plans. And so if there's any questions? If not, then yeah.
Will the BTL layer send messages when will it do the sharing the message before sending it to the peer?
Sorry, I missed the.
Will it sharing the message?
Will it segment the message?
Oh, segment. The BTL does not segment necessarily. So the upper layer is responsible for segmenting. There are a couple of thresholds that the BTL informs the upper layer of. The first is the maximum eager size, which is the maximum message that you can use and expect the eager latency. The second is the max send side, which is the biggest buffer that you can call send on, the protocol where a callback occurs on the receive side when it's sent. Those are probably 1 kilobyte and 4 kilobyte in size. It varies from network to network, but that's about the ballparks you're going to see. And then there's a maximum RDMA, which is the maximum size you can put and get. Underneath, the BTL may segment those further, but the completion callback will be for the entire message. So whatever you called send, that exact size is what's going to happen when you call. Either you're going to get an error saying, hey, dummy, you sent too big of a message, or the receive side is going to be called once with that entire data. So it's up to the upper layer protocol to do any segmenting. Does that make sense? And again, this goes back to there's so many strategies, and which one you want to pick is something that it's very hard for the dummy. The idea was the BTLs are stupid and easy to write because things have gotten better, but we're actually, I showed that big list of BTLs. It used to be about double that size. And so the idea was keep them simple because we have to write a lot of them and push all the complexity to the PML because we only have to write that once. Do you have?
Yeah, I did. You mentioned Sandy a few times.
Yeah.
Is that a company?
It's a federal, what do we call them? It's a federally funded research and development center. So Sandia National Labs is a research center in Albuquerque, New Mexico, and Livermore, California, for the Department of Energy, and it's who employs me. So, but we
Sandia, okay, not
yeah.
Sandia, okay, sorry.
No, Sandia, Sandia. So.